welcome to the 52nd lecture in this series. So I would like to continue where I had stopped last time. So I had introduced this operation of wedge product. One starts with two alternating forms, and one gets by taking the product, one gets an alternating form whose degree is, by degree I mean the number of input variables, is k plus r if they happen to be k and r to begin with. And we essentially use two things to define this: the tensor product and the anti-symmetrization map alt. Now last time I had not written the constant which occurs in the definition, so this time I'll write the constant. So the constant here is actually k plus r factorial, k factorial r factorial. And the reason it's defined like this becomes immediately clear, because alt itself has a 1 over k plus r factorial. So that cancels with this, and one is left with, well, that still doesn't explain exactly why it's defined like this, but at least that part cancels and you end up with this 1 over k factorial r factorial. Now, right, so this let's look at some examples before we move further. So let's take one forms. So let's take alpha and beta to be in L1V, which is V star. I'd like to see what alpha wedge beta is. So alpha wedge beta, and this would act on two vectors. So this should be a alternating two tensor. And I want to see what this is. Now if I just go by definitions, so I can use the last expression here. So this is, so both k and r are 1 here, so this constant in the definition of omega wedge eta does not play a role. So I'll end up with, and again k plus r is 2, so essentially I'll be looking at the symmetric group on two letters, and just there are two permutations. The first one is the identity. The identity gives me alpha v beta w, and the second one gives me, it's a transposition interchanging 2 and 1. Its sign is -1, therefore I get -1, and then I'll get alpha of w and beta of v. Right, so that's it. So the wedge product of two one forms is rather easy to describe. It quickly becomes more complicated as we take higher order forms. Now the other thing we can do is let omega 1, omega 1 omega n be the dual basis of dual basis corresponding to the standard basis E1 up to En of Rn. So IE omega, as usual, omega I eta j equal to 1 if I equal to j equal to 0 if I not equal to j. So let's look at omega 1 wedge omega 2 wedge omega 3 etc. all the way up to omega n. Now I'm being careful in putting brackets around each of these products because at this point we have not proved that this wedge product is associative. So in fact that turns out to be the slightly non-trivial point here. Unlike tensor products where it's quite straightforward to check that it's an associative operation, here it requires a bit of work, and but it is in fact true that the wedge product is also associative. So I don't have to be concerned too much about where I put the brackets. But at this stage, let's keep the brackets and proceed with the calculation. So omega 1 wedge omega 2 and so on. This, I claim that this thing here is nothing but, so this first of all let's notice that omega 1 wedge omega 2 will be a 2 form, alternating 2 form, and then when I take omega 3 it will be a 3 form and so on. So ultimately I'll end up getting, so I don't have to put these brackets at the end. So ultimately I end up getting something in AN Rn. And the claim is that this thing here is exactly the determinant in fact. So let's call this as alpha. Let alpha equal to this. Then alpha V1 up to Vn is nothing but the determinant of V1, the matrix obtained by putting all the columns of all these VI's as columns. So, and how does one prove this? One can try to do this explicitly, but there's a nicer way of going about it, namely first prove the associative property first, prove the associative property of the wedge product, and then observe that once one has the associative property, it will follow that the space of n forms is essentially there's only one element up to scalar multiples, and that's the determinant, and then it becomes a question of determining what the multiple is. That is one way, but the other way is that one doesn't really need that associativity. One can directly try to prove that. Let's check this, the following. To see this, observe that if dimension of V is n, then A and V is, so dimension of A and V is also, not also, it is 1. So on an n-dimensional vector space, the space of forms of degree, alternating forms of degree n is 1. And in fact, even though we don't need it right now, and dimension of A kv equal to 0. In other words, all of these, the only 0 form is contained in these spaces if k is bigger than or equal to n plus 1. So unlike tensor products, you can even on an n-dimensional space can keep on taking tensor products of 1 forms, and you will get as large a degree as you want, order as you want. But for an alternating form, you have to stop at k. If it's more than k, there's nothing other than the 0 element. And let's see this. So the point is that and this computation is very similar to what we did earlier. Let alpha belong to A and V, alpha and beta. To say that a vector space is one-dimensional amounts to saying that given any two non-zero elements, one is a multiple of the other. So let's check that. So alpha, beta. So I start with 2 elements here. And we have already seen in when I did this pullback calculation, that the pullback of the determinant function yeah, right here, in this calculation. So I said that what we in effect proved was that if eta and lambda are 2 elements of A and Rn, and if they agree on this standard basis in the specific ordering, then they agree for all vectors. So in other words, they are identical forms. Here the role of E1, E2, En is the standard basis. In other words, the fact that we started with the standard basis as the proof shows is not that important. One might have very well started with any basis and still the proof works. So in short, if we use the same proof there, we end up concluding that so let alpha beta belong to this, and let V, I already am going to use V for arbitrary vectors. Let E1, En be a basis for V. I mean, since V is any vector space, doesn't make sense to say standard basis. So just any old basis, I will just call it E1 up to En. So I want to claim our earlier calculations show that if alpha E1 up to En equals beta E1 up to En, then alpha is equal to beta. And so now if alpha is not equal to 0 and beta is not equal to 0, not only that, if these two are equal, then this is equal to this, and the value of alpha of v1 up to vn or beta v1 up to vn is essentially, it's a multiple of alpha e1 up to en. So if these are non-zero forms, then on this specific number have to be non-zero. Then alpha e1 en is not equal to 0, beta e1 up to en is not equal to 0. Right. So if this is equal to the so what we can do is, if these two are non-zero numbers, in order to ensure that alpha of this, alpha e1 up to en is beta en, we can just let C equal to alpha e1 up to en divided by beta e1 up to, and let omega equal to C times beta. Then omega then I don't even have to give it a new name actually. So let's just take C, then alpha e1 up to en equal to C beta acting on e1 up to en. Because the way I set it up, these two automatically, this beta will cancel out and I'm left with alpha. So then this. Therefore, now you go back to this remark. The earlier computations show that if this happens, then alpha. Therefore, alpha equal to C beta. So what we have done is shown that as far as the top vector space is, the top degree is concerned, it's a one-dimensional vector space. The space of alternating n forms is one-dimensional. And since we are discussing this, let me also make this point clear. The AKV is 0 if k is bigger than or equal to v. That's also a very frequently used thing. Notice that AKV equal to the 0 vector space if k greater than or equal to n plus 1. This again follows from earlier computations. The reason is, let's go back to that pullback example that I did, and let's look at this thing here. This, what I had here. I started with a form of degree k, and then I wrote eta of v1 up to vk in terms of some constants and the specific values eta of ej1, ejk. Now, if in the number of variables k is bigger than or equal to n plus 1, then what will happen is here there would be at least greater than or equal to n plus 1 entries inside the brackets. On the other hand, since we have assumed that the dimension of the vector space is n, there are only n of these E1 up to n of these basis vectors. But there are n plus 1 slots here which have to be filled out. So there will necessarily have to be repetition in each of these terms. Some EI will have to equal EJ in this. But since eta is alternating, repetition will force the term to be 0. So that is the gist of the reason why for k bigger than n plus 1, AKV is 0. So it just follows by looking at reducing to basis vectors. And there are only n basis vectors, but there are more than n plus 1 slots. So that earlier computation showed us two things. The dimension of A and V is 1. And this we showed by saying that any two non-zero vectors are multiples of each other. Any two non-zero elements are multiples of each other. That's the same thing as saying the dimension is 1. So, and it also showed us that if k bigger than or equal to n plus 1, AKV is 0. Now, but we are at this point, I wanted to claim that, use the wedge product to claim that determinant is the wedge product of one forms which is dual to the standard basis. So I was interested in this actually. So let's see. Right. So what all this we have discussed so far just shows us that this any two one for n forms on Rn are necessarily scalar multiples of each other. So there's a constant such that alpha equal to this. But I want to say that it's actually that constant is 1. So I started with this alpha, which is the so hence what this previous discussion omega 1 wedge omega 2 the successive wedge product is some constant times, hence there exists C in R such that this is equal to times alpha, where alpha is the determinant n form. So I want to say that claim is that this constant is actually C equals 1. And this again, to see this, you just evaluate both sides on the standard basis vectors. So when I do alpha of E1, evaluate both n forms, both sides on E1 up to En. In the right hand side, of course, determinant of the matrix given by E1 up to En is 1, so I'll just get C. On the left hand side, I'll get omega 1 wedge omega 2 omega n, this entire thing evaluated on E1 up to En. And the claim is that this is actually equal to 1 as well. So this is 1 and the right hand side will give me C. So therefore you will be done. Now to see that this is 1, you just one proceeds step by step. So call this as beta n minus 1. So beta n minus 1 wedge omega n So this is a n minus 1 form. That's why this index is that. And E1 up to En. This is by definition n factorial by n minus 1 factorial. And then of course this is a one form, so this is sigma n Sn sine sigma beta n minus 1 E sigma 1 etc. E sigma n minus 1 multiplied by omega n of E sigma n. Right, so this is just the definition. So here I can just write n times some stuff here, sigma n. Right. Oh, actually there's no n factorial, that got cancelled with the alternating thing. So it's actually, so 1 by n minus 1 factorial. And then now notice one thing here, omega n is the dual basis. So and this term here will be non-zero if and only if sigma n happens to be n. For if sigma n is not n, then this is 0. So it will only survive for those sigma such that sigma n equals n, and then sine sigma, then beta, and then it will be 1, beta n minus 1, E sigma 1, E sigma n minus 1. So what one ends up with is essentially 1 by n minus 1 factorial. So this all those permutations of Sn which fix n, this essentially can be identified with sigma n Sn minus 1, one lower down, and then sine sigma remains the same. Then one has beta n minus 1. Everything is the same except that I am now looking at this. So in other words, right, so I end up with this. Now you go back to the, again, so it's a inductive process. So now you go back to beta. What was the definition of beta n minus 1? It is omega 1 wedge omega 2 all the way up to omega n minus 1. So what one wanted to claim was that this thing here, omega 1 wedge, this entire thing is equal to 1, and what we have done is we evaluated it on E1 up to En and then reduced it to a sum involving beta n minus 1, and we have restricted the permutations to Sn minus 1. The point being that I can again write it as this thing here as a wedge product. So this would be 1 by n minus 1 factorial sigma n Sn minus 1 sine sigma, and then this beta is, so I can call it again this as beta n minus 2, beta n minus 2 wedge omega n minus 1 acting on this, the same stuff. Again, so when one looks at this, one will get exactly one term which will survive. No, not one term. This only certain terms will survive here, and one can proceed like this. However, so we'll stop here, and in the next class I'll resume at this point, and then I'll list down the basic properties of the wedge product that we'll be needing. I may not be able to prove all of them, as I said. All right, so thank you.